Okay, now I want to discuss something called the Coulomb logarithm. And uh, this is going to come about when we actually try to apply the formula we have for a single Coulomb collision to the case of any kind of ensemble of particles. And the reason for that is in a single collision, we took a particular impact parameter and a particular velocity. And now in a realistic medium, you're going to have particles with different velocities and different impact parameters. So you would have to do some kind of a weighted integral over these two quantities to be able to get, let's say, the emissivity of a medium. And you know how to do things with velocity, right? I mean, you basically assume a velocity distribution and you'll go through the integrals. We'll do that later, but first let's look at the integral over the impact parameters because that's something new to you. And that's where we're going to encounter something called the Coulomb logarithm. Okay, so I'm going to start with the expression we had for the spectrum of the emitted radiation due to a single Coulomb collision. And I'm just going to take the simple form of the expression where it's kind of a step function. It's a constant value up until a certain frequency in the low frequency limit, and then it basically drops to zero instantaneously. Now notice that I've, instead of saying omega far less than v by b, I've just said b far less than v by omega. And you know, this will become obvious when we actually go through some more steps here, why I've cast it in terms of b and not in terms of omega. Anyway, our focus right now is on that b, how things change with that impact parameter, and how we can, you know, take an ensemble average over all different values of impact parameters. Now, let's say for the sake of argument, you want to calculate what is the emissivity, the Bremsstrahlung emissivity of a medium, right? So you were trying to calculate the amount of energy emitted per unit frequency, per unit time, per unit volume, per unit solid angle, okay? Now, again, just for simplicity, I'm just going to say that the emission is isotropic, okay? And, you know, in reality, the emission from a single collision is obviously not isotropic. It has a characteristic dipole emission pattern. But eventually, let's say you apply it to the case of a medium where the velocities of the different charges are all isotropically distributed, right? So in that case, the sum total emission will become isotropic, even though the emission of a single collision is not isotropic. So anyway, for now, I'm going to assume, you know, I'm just going to divide that by 4 pi and say that's the amount of emissivity, or let's say the power per solid angle, right? So I've just assumed an isotropic case. Now I want to bring this in terms of omega and not nu, angular frequency and not the frequency. So I've just put the Jacobian 2 pi here. Now essentially I have calculated dW, which is the amount of energy emitted per unit angular frequency, right? This has been calculated for a single Coulomb collision. Now all I have to do is I need to find how many Coulomb collisions happen in a given medium over a time interval dt and over a volume dv, right? And then I'm done. I basically get to the emissivity. Okay, so let's see how many Coulomb collisions happen. Again, this is, you know, there's no physics here in calculating it. It's just basic bookkeeping, right? You're just trying to account for how many collisions are happening. So just take a small volume and imagine that a single electron is going through this volume, okay? And imagine that all the protons in this volume are going to project annular disks in front of them, rings, sorry, in front of them with the correct impact parameter for which you're trying to calculate the number of collisions, okay? So we're going to calculate the number of collisions for a given impact parameter. And to be more mathematically rigorous, we're going to do number of collisions per unit interval range and impact parameters. So if you want, what we're doing is number of collisions divided by d of b, right? So the differential amount, the differential spread in the value of the impact parameter, okay? Now, I can write that down as the total number of electrons in this volume, where V is the volume, Ne is the electron volume density. So that's the total number of electrons in this volume multiplied by this factor here, which I'm going to show to you, is the number of collisions or scattering events of a single electron. Okay, so this is going to be the number of collisions per electron, and I multiply that by the total number of electrons to get the total number of collisions inside this volume. Okay, so for a single electron, you know how to do this, right? When we did absorption coefficient, we kind of did a very similar calculation. Um, so if you take the ion density, Ni, which is the density of these scattering centers, times their cross-sectional area, which is 2 pi b times dB, right? So that's density times their cross-sectional area. This actually is analogous to the absorption coefficient which you had, right? So cross-section times the density. So in some sense, it's the scattering coefficient, right? So this is per unit distance. This tells you, this basically tells you the cross-section for scattering per unit distance traveled by the electron. And then I'm going to multiply it by the distance traveled by the electron. Then now I basically have the number of electron collisions, right? This is per centimeter, this is centimeter. So here I get total number of electron collisions. Again, I multiply that by the total number of electrons which are moving in this volume. So I get the total number of collisions, right? So I'm basically done. So I can write the emissivity here as basically the value which I had for a single charge, which is dW by d omega for a single electron. And then I need to now figure out how many collisions are there per unit time per unit volume, right? So I just bring the per unit volume, which is V here, and per unit time, which is delta T here, onto the left-hand side. And whatever is left on the right-hand side is the number of collisions per unit time per unit volume. Okay, so I just do that. You can, pause the video and then make sure you understand the algebra here, and then I get an expression for the emissivity. Now, if I plug the value which we calculated for a single Coulomb collision, and then figure out what the emissivity should be. By the way, now I've written the emissivity as an integral over all the possible impact parameters, right? So we just calculated all of this as number of collisions for a given impact parameter. Now I need to integrate over all impact parameters, so I get the total emissivity. Now we are taking care of all possible impact parameters, right? In an ensemble sense, in a statistical sense. Okay, but so far we haven't taken care of all possible velocities. Okay, we are still assuming that there is a velocity which all the electrons have, which is V here. Okay, so if I then tell you that, oh, there's also thermal distribution of electrons, then you'll do another ensemble average over all the possible velocities, and then you'll get the value for the emissivity. Okay. All right, so what do you end up with? In the end, this factor here, if you remember, had a b square in the denominator. Now we have a b here. So you end up with some kind of an integral of dB over b. And that's where the logarithm comes in, because the logarithm of 1 over, the integral of 1 over x is logarithm of x, which means now we need some minimum and maximum, ranges here to properly carry out the integration. And I'm going to call it B min and B max, and then that gives you the emissivity. And this factor here is called the Coulomb logarithm. And what value you choose for B max and B min, again, is a matter of, it depends from circumstance to circumstance. And so the Coulomb logarithm, which you will use, also will depend on the circumstances in which the approximation you're making are valid or not valid, or those kind of things. So I'll give you a few examples to give you a sense for what these values are. Now, B max, notice if you're using the low frequency approximation, then B max will have to be V over omega, right? That basically comes from here, from this. So what this is telling you is that if you're interested in the free emissivity at a frequency omega, and if V is the characteristic speed of electrons in the plasma, which is emitting, then if you have an impact parameter which is much larger than this B max, then you're not going to get much contribution at this frequency omega to the radiation, because you're going to just violate this condition, in which case the emission is almost zero, right? So we have a natural choice for B max for the maximum impact parameter, and that just comes from the low frequency approximation. Again, that might fail if you're interested in higher frequencies, right? Then this is going to fail. Now, what about B min? Well, there are a few ways to specify B min. One obvious way is to say, well, B min can't be smaller than the uncertainty principle, right? So you have delta x delta p is equal to Planck's constant. The momentum here is kind of mass times the velocity of the electron which is coming in. And then you can say that if I have an electron that's coming in with this momentum, I will be unable to locate it to a distance which is more accurate than delta x, and I'm going to call that the B min, where the classical treatment is just going to fail, because if you want to go below B min, then you basically have to treat all of this, quantum mechanically, right? I mean, none of this is going to work properly. So, and then when when you're trying to treat this quantum mechanically, the crudest approximation you can make for B min is to call B min equal to H by mv, right? So that's the crude quantum mechanical approximation for B min. Now, even classically, you will recall that we made this assumption that in this kind of Coulomb collision, that the electron is almost going in a straight line, and it's really the y-axis jiggling of the electron, which is important. The trajectory is almost a straight line. Now, if you go to very small separations, then that's no longer true. You need to really take into account a curved trajectory which the electron is going to have around the proton. I mean, the electron can also get captured and go into orbit around the proton. So if again, there is another B min there, which you can plug in, which says that the minimum value of impact parameter for which the straight line assumption fails, I'm going to call that B min here, and you'll get a slightly different answer. These are all different approximations, right? Another B min you can put in here is to say that B min should be less than the Compton wavelength of an electron, right? And if you have a B min much less than that, then of course you can't, the electron is no longer a particle, right? I mean, you have to worry about the fact that it's a wave and it's not a particle. So there are many different choices for B min. So there's no one value for the Coulomb logarithm. Again, all of what value you use here will depend on whether a quantum mechanical description is important for the scattering, whether the low frequency approximation you make holds or not. So it is in the end going to depend on the frequency at which you want to calculate the emissivity for, and it's going to calculate and it will depend on the velocity range of the electrons, whether quantum mechanical treatment is important, whether a classical treatment will do, those kind of factors. So the way we deal with all of that is to sweep all of that under the rug and then call something the free Gaunt factor. And that is defined as square root of 3 by pi times the Coulomb logarithm. And so the way we want to deal with it is to say, okay, let's retain this form for the expression, right? Let's retain all of this. Just to calculate this Coulomb logarithm, I'm going to have to do much more complicated physics. Maybe I need a full quantum solution. And so I'm going to do that separately. And then I'm going to plug that into this expression and call it, and that correction which you're going to plug in is called the Gaunt factor for free emission. Okay, and you can easily find tables for Gaunt factor. And in this course, we are not going to go into details of calculating the Gaunt factor because it will take us too far afield from what we need to do. So yeah, just be aware that you will be using, if you're doing this kind of research or calculations, you will probably look up tables or expressions or approximate expressions for different Gaunt factors. And the kind of considerations that go into calculating them are what I outlined here. Whether the approximations you made are fine, whether you can treat the electron as a particle and not as a wave, whether you're violating the uncertainty principle in some, in this crude way which I just showed. All of those things go into consideration in actually calculating the Gaunt factor. Okay, I want to do one more thing of theoretical interest in case of Bremsstrahlung. And I want to do this because the technique which I want to talk about is actually of much wider applicability than just Bremsstrahlung, and it's called the method of virtual quanta. And it goes something like this. So let's apply to the case of Bremsstrahlung as a case study here. So let's say you want to do relativistic Bremsstrahlung, right? So you have a fresh problem now, which is, so far I've assumed that the Coulomb potential of a proton is basically that nice radial Q over R square, Coulomb force law, right? That's what I've been using. Now let's say that the electron is relativistic. It's moving relativistically. Let's say the proton is heavy. So let's say it's not relativistic, but let's say the electron is moving relativistically. Okay, now you have a problem because the Coulomb potential of the proton is not going to appear in this nice radially symmetric way to the electron, right? You did calculate that the electric and magnetic fields do Lorentz transform. So in the frame of the electron, the proton is not going to look the same. Its field is not going to look the same. So how do you deal with the Bremsstrahlung scattering? So one way to deal with this problem is to go into the electron's rest frame. So let's say you're in the rest frame of the electron, which means that you are at rest and you see a proton approach towards you at a relativistic speed, right? So this proton, if let's say your velocity was 0.9 times the speed of light, in your rest frame, you see a proton approaching at 0.9 times the speed of light. Now, okay, that's fine. So what happens then? Now, you know how the fields of a proton are going to look to you. Okay, in the rest frame of the proton, of course, the fields are radially symmetric, but in the electron's rest frame, those fields are highly they have a very pointy shape, right? So the electron actually feels a pulse. We calculated this last week, right? We actually calculated the exact analytic form for that pulse. So now the electron feels a pulse of electric field directed towards it at the point of least impact, right? So right at the point of closest approach, the electron is going to feel a sudden electric field pulse. Now, one way to deal with the Bremsstrahlung emission is to sort of in terms of just the intuition, the way to think about this is that this pulse, this electric field pulse is composed of virtual photons. I say virtual because this is not a radiated field. This is not a field which is an electromagnetic wave carrying energy. So they're not real photons. You can think of them as virtual photons, okay? And these photons are just, they're just existent there. They're not traveling anywhere at the speed of light, so to say. And they're just moving with the proton, right? So they're kind of cohorts of this proton. It's just a, how do you say, it's a quantum way of thinking about the electrostatic field of a proton, right? So there's no acceleration, so there's no radiation. It's just that this proton has like an entourage of virtual photons, which is going with it. And then we know the cross section an electron presents to photons, right? We calculated that. That was the Thomson scattering cross section. So look at this equation. Okay, in this primed frame, the primed frame is the frame in which the electron is at rest. I'm going to make the following statement. So the spectrum of radiated energy, that's amount of energy radiated per unit frequency, is equal to the Thomson scattering cross section times the amount of energy, the spectrum per unit area of the electromagnetic pulse which the electron feels. Okay, so D, this is energy per unit frequency per unit area, right? So the areas cancel out, right? So this is the pulse you feel per unit area, and the size of the electron is the Thomson scattering cross section, right? That's the meaning of the Thomson scattering cross section. It is how big an electron looks to photons, or how big an electron looks when it's trying to scatter electromagnetic energy or photons. That's photons see an electron and they see an obstacle of this cross section, right? That's what they're kind of intuitively understand. There's an intuitive understanding, of course. That's what the photons see. The photons see that the electron is so big, right? And so if you just take the number of virtual photons per unit area and then say that multiplied by the Thomson scattering cross section, that fraction of photons are just going to get scattered or emitted by the electron in the form of Bremsstrahlung. Okay, so this is a very kind of a piecemeal intuitive way to look at Bremsstrahlung emission, and it turns out to be incredibly powerful because you actually end up getting the right answers by looking at things this way. So, which also tells you that you can actually, instead of just saying that this is a piecemeal approach, think of Bremsstrahlung as the scattering of virtual photons by a charge, right? You can actually frame the problem of Bremsstrahlung as scattering by charges of virtual photons. Okay, so let's actually work this out to show you that in the end we'll end up with an expression for this, which is is actually the same as what you had when we did the calculations, let's say in a completely first principles kind of way, like this kind of expression. So it kind of puts this approach in equal footing to the approach which we have already taken. It's just as valid to say that Bremsstrahlung is the scattering of virtual photons by charges. Okay, so if you go back to your notes, you know that in the primed frame, so in the frame in which the electron is at rest, you're basically calculating the charges of let's say a relativistically moving charge, right? And you've already done that. We did it last week by using simple Lorentz transformations. We just took the electric fields of a charge at rest and Lorentz transformed it to another frame. And so you ended up with this, where gamma was the Lorentz factor, V is the speed of the charge, T is time, and B now is the impact parameter, right? B is the y-axis value at which you measured the fields, which is now in our case the impact parameter. Okay, so you had an X component of the field, Y component of the electric field, no Z component, and then you had a magnetic field. Now, of course, the magnetic field is not important for us because the electron is at rest, right? So it's not going to experience some kind of a magnetic Lorentz force. So we only have to worry about these electric fields here. Now again, if you look at the equations for this electric field, of course, they look very similar to the equations you had for the acceleration when we actually did Coulomb collisions in the previous video, right? So they really look like this odd function and even function. X is an odd function, Y is the even function. And again, I'm going to make the same approximation that in the dipole approximation, yeah, you don't have to worry too much about the odd function. Actually, the beautiful thing about formulation in terms of virtual quanta is it allows you to actually go through the derivation while taking into account Ex also. Okay, I'm just not going to do it for simplicity. You don't even have to say that because this is an odd function, I'm going to throw it out. You can actually take Ex into account and go through the calculation. You can actually go through the full calculation in closed form. Okay, so what do I want from it? I mean, these are time domain quantities. I actually want the spectrum, right? So this is the time domain pulse that's coming. I want the spectrum. I'm going to take the Fourier transform, of course. Okay, so here's the Fourier transform of EY. You could do the same for EX. Okay, you could do the EX also in closed form. But okay, I'm just going to do EY because that will end up being the dominant term. And again, this integral here is going to be the modified Bessel function of second kind. And you can go through the algebra here and pause the video and have a look to make sure that this equation is right. So that's the electric field pulse, right? What do I want? I want the power per unit area per unit frequency. Sorry, the energy per unit area per unit frequency. Well, that's just the Poynting theorem, right? In the Fourier domain, the Poynting flux in the Fourier domain is C times E hat square. Okay, so I multiply by C and square this value. You basically get the quantity which you're after. Okay, that's the quantity which you want to plug in here. Multiply that by Thomson scattering cross section. You're done, right? It's actually simple. You're done here. Now, all of these are in the prime frame. Okay, notice that I said omega prime, right? All of these are prime quantities, E prime. Because now you're still in the frame of the electron, right? The lab frame is not the electron frame. The lab frame is actually the proton frame, because the proton is this heavy particle which is at rest, and the in the model we have, the protons are just fixed and the electrons are zooming past. So we need to now go from the electron frame to the lab frame, which means I need to go from the prime to the unprimed frame. Okay. Notice also that I didn't say B prime here. I think that should be obvious by now, because B prime is equal to B, right? That's not along the Lorentz boost. So there's no length contraction in a dimension perpendicular to the Lorentz boost. But of course, the other quantities have to be transformed. Omegas have to be, the frequencies have to be transformed. The energies have to be transformed, all of that. Now, energy transforms as the time component. Frequency also transforms as the time component. So that's simple. These two are the same. You can remove the primes. What about here? Let's see, we have omega prime here. Well, that's where, you'll transform according to the Doppler factor. So now the way you transform this depends on the angle at which you're observing it from, because the Doppler factor has a cos theta in it. And then you're done basically, right? So this is your expression. If you actually write down the Thomson scattering cross section in terms of the basic constants, you'll actually see that this expression is basically similar to what we already derived. But now we've done this using this idea of virtual quanta, which is as bit a fundamental way of looking at Bremsstrahlung as we have done before. So yeah, so that's a very nice way to derive these things with virtual quanta. The advantage of this is that it allows you to take into account the effects of aberration, right? And the effects of transformation of electric and magnetic fields, which you couldn't in the previous description, right? In the previous description would actually fail if the proton were relativistic, but sorry, if the electron were relativistic. But this description doesn't fail. This description is completely okay with the electron being relativistic. The only assumption we are making is this kind of a large, this assumption that the electron is basically going on a straight line, right? So we are still making the assumption of a large impact parameter. Otherwise, you can't transform into a single rest frame for the electron. The electron actually is an accelerating body. It's not just going in a straight line, it's actually accelerating. So you need to take more different things into account. So, this makes slightly different assumptions, but it gives you a way to deal with the aberration of the pattern of the electric field because of relativistic effects. And this is probably the easiest way to deal with that kind of aberration is to use the method of virtual quanta. Okay.